welcome to this Intercem LC3 Day webinar. Wherever and whenever you're watching this live or on demand, I would like to thank you for joining us today. In this session, we'll have a world exclusive first look at two hugely exciting industrial scale LC3 projects by Çimento Global Holdings in Africa. And we are honoured to have with us today Berkan Fidan, Performance Director and Process Director of OYAK. Unfortunately, the other advertised speaker, Suat, has had to send his apologies and is unable to participate today. I'm Matt Owen, Head of Conference Operations at Intercem, and I'll be your host. And also joining us for the Q&A section of this presentation is Malcolm Shelball, Chief Executive of Intercem here in London. I'm sure that you'll have many questions about the presentations and these exciting projects that you would like to ask Berkan, and to do so you can use the Q&A button at the bottom of the screen. Remember you can put your comments or questions anonymously if you wish to do so. You can also download a copy of today's slides or rewatch this presentation with your free pass today. With that, I'd like to introduce you to Berkan, and Berkan, I'd like you to introduce the presentation and to share your screen when you're ready.
Okay, thank you, Matt.
Okay, we've not got that full screen, Berkan, so if you want to, yeah, that's perfect.
Yeah, okay. I can start, just Matt?
Yes, that's absolutely fine. We can see the slides and we can hear you loud and clear. So when you're ready, if you'd like to start.
Okay, firstly, good afternoon and welcome to all participants for this webinar. It's also exciting for us to attend it. I'll start with just a note of our chairman. Our chairman, Mr. Suat Chalbi, could not attend today, but he shares his greetings and transmits a few remarks. I want to just start with that remarks to all participants. He just said it's about our remarks about our strategic perspectives and the other issues we wanted today. And this is just to provide the background to the panel on today. When we look on our Çimento Global Holdings is sustainability. One of the important pillars of Çimento Global Holdings is sustainability, either environmental, social, and economic. Our main target is to contribute to sustainable economy to guarantee the future of the whole planet and of the upcoming generations. We are committed to playing a pivotal role, the circular economy for 20 years, and Çimento is also a founding member of Cement Sustainable Initiative, together with 9 more large multinational companies in the sector. An action plan was launched and a joint commitment to the principles of sustainable development. According to our group level long-term strategy, we continue to invest, reduce CO2 footprint in light of developments of Paris Agreement and the EU Green Deal and the EU 2030 climate target plan. We are also cooperating and developing together with universities to produce new kinds of clinker with less CO2 emissions, as well as considering new disruptive technologies. Our long-term strategy encourages to increase the alternative fuel substitution rates, energy and resource efficiency, and the new type of cement with less clinker incorporation, namely using calcined clay and other supplementary cementitious materials. As a conclusion, I would like to stress that the acceptance of calcined clay blended cement as a viable material would lead to clinker content, reduction in the cement blends, and reduced CO2 footprints. I would like to share with one of my favorite quotes from Barack Obama. We are the first generation to feel the effect of climate change and the last generation who can do something about it. With kind regards. Thanks again. It's just the remarks and notes from our chairman about that, Suat Chalbi. Now, I want to just start today's topic about our case study and just details about our project, Calcined Clay project. It's our project. We named this. There are many names available. It's known as Calcined Clay. Calcined Clay added cement is known as LC3. Our name is DeOHclay. We named it. It comes from dehydroxylated clay because of the main reaction of that process. And today I will present our project about that and our experiences and some details, technical details about these issues. I will start with just current cement production and CO2 trends. In the first session on this morning, Professor Scrivener also just told many details about that, but I just want to talk about a little bit. And as we all know that cement production is growing up, and it's expected that between 12 to 23% by 2050, it's just increased, grow up. And direct CO2 emissions from the cement industry are also expected to increase by 4% globally. And when we look on that, low carbon transition in cement industry becomes much more critical than ever with upcoming years. And there are many actions available done by the 2 degrees Celsius scenario and also the reference technology scenarios. When we look on that scenarios, it's the gap to decreasing the amount of direct CO2 emissions related with cement. The main topics, the main 4 topics, it seems like it's thermal energy efficiency, fuel switching, reduction of clinker, and innovative technologies about carbon capturing. The most active, it's around 48%. It will be done by carbon capturing and related technologies. But as all we know that it's just new technology and it's expensive. It's currently its feasibility. It's not good on cement production, but it will become much more proper in next years. But still, it's a developing technology. In the second stage, it's the most effective one, the second most effective one with 37% on this decrease is reduction of clinker. And that's the reason that we focused on more about that, the cementitious materials to change the content of clinker in the cement and to decrease the carbon effect. Again, it's just shared with Environmental Energy Agency, International Energy Agency roadmap. It's given in here. Just seen it's a data of 2014, but it's nearly similar for these years also. The main component of cement, it's just clinker, as we know that, with 65%. And the other components, besides gypsum, it should have to be. But the others are, as you could see, that it's limestone, fly ash, blast furnace slag, and steel slag, and some natural pozzolan. But the natural pozzolan amounts are located in different regions, but its abundance is not so effective. It's less in some regions around the world, and also reserves start to deplete. On the other side, the most used ones are blast furnace slag and fly ash. As we know that just because of that CO2 actions, these plants also starts to close, and that secondary output of their fly ash and blast furnace slag also will be decreased in next years. At that point, the last point is limestone, and the other fillers, but these are not reactive as the others. It's just working as a filler and very tiny effect on the clinker strength and other issues. Then we need an additional material, and it should be abundantly available in all over the world. At that point, calcined clay become a potential in here, and just lower clinker ratio could be achieved by that thermally activated clay composition. And it's just also has a higher effect on strength with when compared with limestone and the other filler components. The new supplementary cementitious material is dehydroxylated clay, just based on the thermal process with known clay minerals. The well-known clay minerals, is, as we know, it's highly available in all over the world. Is kaolinite, illite, vermiculite, smectite, and chlorite are the main types. These are, but the crystalline structure is critical in here due to its one-to-one structure of kaolinite in one tetrahedral sheet and one octahedral sheet effect. It becomes, after reacted with thermal, after dehydroxylation, it turned to the metakaoline. Metakaoline is a known product. Its reactivity is well known, but generally it's produced with high purity for different mineral processing industries. It's partially used in cement industry because of its high quality kaolinite required to produce that material. But in that part, the low quality kaolinite with 35–40% kaolinite included clays can be used in cement industry. And it's its decomposition, it's like that. It happens in, starts in just near to 5,000 degrees, the delamination happens, and then after that it turns to metakaolinite since it reached to the 650–700 degrees. According to that, specific types of clays, also its thermal activation, and that activation issue is also need to be checked on process side. On that point, when we check the specific clay minerals, it's the critical point. It's just there is a hydroxyl group removed in some temperature, but then if the temperatures start going to increase again, a crystallization happens in all these clay minerals. And the range is critical because in industrial scale, to produce a product like that, to make the dehydroxylation in the industrial scale, you need to have a range in here, because process control and keeping the range and getting the best reactivity is critical to do all the dehydroxylation completed, but not reached to crystallization phase, because in crystallization phase, it's just mullite and spinel formations starts to appear. These are coarse grains and without any hydraulic reactivity, and it decreases the quality and effectiveness of calcined clay as a cementitious material. On that point, the range, it's just the range when we check, it's the largest range is available in kaolinite, as you can see from here. And just in the illite part, it just, again, it's a secondary potential one, but it's 2-to-1 group clay. Its reactivity is much less than kaolinite, but it could also effective if it includes in the clay. And then the montmorillonite, but the critical part for montmorillonite is very narrow range, and the temperatures also increased when compared to kaolinite. That means higher heat requirements in that group. And just according to that, we checked the abundancy and the suitable clays around the targeted regions. Quality of dehydroxylated clay is directly related with raw clay characteristics, as I told, in process conditions. And there are some states and just size decreasing and just sieving and screening the unreactive components inside the clay need to be removed if some inhomogeneity is available. And then drying and then dehydroxylation is the process of it. At that point, the color is a critical point with clay because it includes iron oxide content inside of it, and oxidization of iron oxide after 500 degrees, it creates reddish color due to the formation of hematite. And that point, there should be a reducing atmosphere to control it. If the process could be controlled and done in reducing atmosphere, then its color becomes much more darker. As you could see, two samples in here, just one in the completely reduced atmosphere to them, the other in the oxidized one. It's according to the amount of iron oxide content, it goes from pinkish to reddish colors. On the right side, you can see that it's our actual product in Abidjan plant. It's dehydroxylated clay. at current startup period, commissioning period, we didn't apply that reducing conditions yet, but we controlled the amount of iron oxide content. That's the reason that it's not so reddish. It's like for cement industry, it's a known color. It's like raw meal color. It's just that color. And the other part is also exactly produced products. As you could see, the color effect with 20% added, not a big effect on the color, but by the control of additional reducing conditions, there will not be a problem about the color issue. As I told, it's the quality of DeOHclay clay is critical, and we also checked and studied on it since the beginning of our projects on it. And as you could see, some samples about it. And the critical point is just thermal change and with increasing temperatures, and also the gravimetric and the removed loss on ignition part is also critical, need to be checked before just using that raw clay. And also while processing, it should be a control parameter. It's just an example of it, that as you could see, when we heated up the material, just at the first less than 100 degree up to 100 degree, it's some interlayer water evaporated, and then there's an endothermic reaction. It's happened in here, and it just related about the gibbsite and the goethite contents in our composition, and some clay minerals also could include it. But after that, the other peak, just after 400 degrees, it starts to make a peak, and that's the kaolinite. And that's the amount of kaolinite happened in here. Then after heating up, it continued. When we reached the over 950 degrees, the exothermic reactions are started. That means the crystallization and new phases starts to appear, like cristobalite, mullite, and other spinols. That means it's just we're starting to lose its reactivity. On the other side, it's just chemical composition and oxides are also critical. You could see that there is a chart. It's just we followed in here, and we just try to define the correct range of materials. There are some exact samples from the field. I showed it, but 3 pillars in here. It's important. That's LOI, aluminum oxide, and aluminum silicium oxide ratio to just check and need to be select the correct material. Now, after that quality details, I want to just talk about our projects in Africa. It's just why Africa, it's just why we selected Africa. Just start with that one. The first issue is that CO2 emissions is critical for all over the world, not only in the Europe, China, or it's just they are the pioneer about that issue, but the emission happens in everywhere to a single atmosphere. At that point, we have to decrease CO2 emissions in everywhere. The other issue, when we check the Africa potential, it's population increase, developing, and the demand to cement and construction materials. It's generally, especially the mid and west part of Africa, it's the big importer with clinker, bag cement, and bulk cement, especially from Europe. And the south part, there are some clinker producers, integrated plants available, but again, some material comes from Asia and Middle East. In the northern part, has much more chance because of that raw material availability. Clinker can be produced in here. At that point, we focused on West Africa because of its developing position and its potential in here. And it's related about also, in the right side, you can see that the calcium carbonate content in Africa continent. As you could see that it's the northern part, it's highly available calcium carbonate reserves, but especially in the sub-Saharan region, its calcium contents are very low. And that's the reason that the main component, calcium oxide, couldn't be available in here. And integrated plants are very few plants, or some countries couldn't have chance to produce clinker. That means all the material need to be imported. One issue is that they're not producing, and also the logistics, just getting that clinker, getting that cement to you also cause an additional indirect CO2 effect to the atmosphere. When we look on the kaolinite, as I told, it's the most reactive material when calcined, when DeOHclay. It's kaolinite. It's highly available in West Africa on both in topsoil and subsoil regions. As you could see that it's yellowish color. It's just means the kaolinite, especially in the subsoil in all over the Africa, but also in topsoil in West Africa and the Middle Africa. Just it's available kaolinite. That's one of the other reasons, the potential of that, the potential and the reason of our selection of West Africa. By that way, they could produce their own cementitious material rather than getting clinker, limestone, gypsum, and everything from outside. Just a little bit detail about the soil formation of Africa. Again, just supporting our decision. As you could see that it's just there are soil types on the right side. It's just ferrosols, acrisols, nitisols, lixisols, and luvisols. There are soil types, and these are generally including rich kaolinites and some other reactive clay minerals inside of it. When we focus on it, also it gives an idea. It gave an idea to us. Just we need to focus that region in the West Africa, just around that region. It shows that it's abundantly available potentials in here. Now, I want to just talk about the production technologies. As you just, we have two projects in Africa, one in Abidjan plant. I will share the details of that plant in next coming slides. It's in Ivory Coast, commissioned in August of this year. And still we're producing calcined clay in that plant. It's based on a rotary kiln and rotary dryer option. And there's also an upcoming project will be completed end of next year, and it's based on flash calciner. We selected, there's also very discussions available still on the industry and the supplier side, just selecting one. But we selected both of them. That's because our strategy is based on experiencing in real industrial scale to both options, because we believe that we need to see on the industrial scale to do the best. We are not getting only the equipment and technology. We just directly involved in design and R&D processes in both projects with that suppliers. We participated since just survey mining details to finding the material on the field, to the tests, pilot scale tests, to checking color control issues, the hydroxylation processes, and the other details. And also we are studying upcoming grinding requirements and specific grinding details technologies about that. Just some small notes about according to experience for rotary kiln and rotary dryer concepts, just with our experiences since the commissioning. It's also a simple design, and it's a well-known process, as everyone knows that rotary kiln and rotary dryer is a known process for cement producers. Wide range of feed size. You don't need to just decrease the size so fine or just doing it, but there need to be some homogenizing and just not sending the lumps to the inside the kiln, because of it affects the reaction and heat transfer. But size range is not so critical. There's a flexibility on it. And again, moisture content, it's just up to 27% can be fed into the kiln. It may affect your process conditions and capacity, but you could just produce calcined clay flexibly with that material. And also, if just the moisture content decreases, that means also an advantage. You could increase the capacity. There's also a potential on it with that type of technology. When we look on the disadvantage, it's just the lower sensitivity on process control. That's the issue. That's related about with the kiln retention time and fill tube design of it. If your material fluctuates so much, that creates problems from the process. Color control, it's a little bit complicated because there's direct flame. You need to create a reducing atmosphere, but you couldn't measure inside the kiln. The only point is the outlet point to create both reducing atmosphere, but it creates some safety risks. You should have to control flame and the combustion process. without getting to danger point. You should have to create controlled reducing atmosphere required. The also uneven thermal effects of over particles, just because of laminar flow inside the kiln. It's it creates some overheated particles and just non-dehydroxylated compositions. Its range is large. And as I told, the direct flame and secondary air adaptation, it's a disadvantage on that point when compared to the other option, other technology. And fuel flexibility, there need to be some specific preparation and combustion requirements, like just getting dedusted and just hot secondary air to burn specific type of coals or pet coke or other thing. It's not, there are some efforts required on that point. And one other thing is there's a potential of agglomeration and ring formation. If any fluctuation in the material or fuel or on the process, it's a risk. Like all the kilns, it's unstable process may cause problems like that. When we look on the flash calciner, I added that point. It's just our aspects, and according to our pilot studies on it, this is our remarks and comments over it. Flexibility on process, effective heat transfer due to dust and gas transfer concept. Various fuel options can be used. The efficient heat recuperation can be applied because on the same tower you can do it. Also, reducing conditions can be controlled and done effectively because it's just, as we know from our creating towers from cement industry, you could control reducing atmosphere, measure it, the temperature, gas measures, DPs or everything on the tower wherever you want. And you could also add some fresh air or some other things on the tower to control reducing and oxidizing atmospheres. That's also an advantage. And there's not a rotating parts that's available on open basis. It just also helps the maintenance process, maintenance requirements, and just preventive maintenance issues, much more easier at that point. Also, there are some equipments like requirements like crushing with hot air and fan and other things. These are specific equipments, but in generally, it's not rotating the main body. Disadvantage, it's due to air flow, it's gas flow issue. The fine feed size, it's required less than 2 millimeter. If achieved, is less than 1 millimeter. That needs a pre-process on it, and it means that pre-drying and size reduction required. It's an A-coupled, can be done in A-coupled or separately, but better between A-coupled to use the heat from the tower. There should be a larger system one with high DP potential. It causes a high electricity consumption, the other issue. And also vertical construction and civil works. It's much more complicated and when compared to the rotary kiln design and layout. Now I want to just introduce the first calcined clay blended cement certificates. We got it in our colleagues in Ivory Coast got it, and there's two, you could see the exact certificates for SEM2BM QL and SEM4BQ. It's just marketed. We just in the right side you could see the cement packs. One is for SEM1, the other one SEM1 42.5, the other one is SEM2AL, the introductory products. Now we will just add the other two products with calcined clay, and we introduce the market. And our aim is just to make it the highest sale with that, doing the sale with that type of cement for 42 point and 32 point strength classes. I want to share some results. We could say the first industrial, not the first. It just we produced calcined clay, but we started to produce that cement just last month, and we got the first results about that. These are really promising results. We got it, and when compared with SEM1, the blue column, and the other one is the gray column, it's SEM2AL with limestone added cement. As you could see that it's in 2 and 7 days, it's nearly similar to the SEM1. It's just a little bit low than that. But in the 28-day strength, we got a better performance when compared with someone. This is the first receipts we used is around 20% calcined clay and 10% limestone added. The standard limits it's up to 35% without gypsum, as we know, and we are planning to just force it on that point. On the other side, the other product, SAM4, we are planning to increase the amount of calcined clay much more than that. Just when we look on the CO2 reduction and CO2 footprint effect of dehydroxylated clay, DeOHclay we produce, as it's a data of that plants, Abidjan plants in the imported clinker and used one. As you could see that the OPC it's around more than 700 kgs, 700, 750. And just mid-blended cement with calcined clay, SCM-2 group, as I explained to you, just we could decrease around 600. And with high blended group, we could decrease less than around 400, just under the 400 kgs CO2. It's also related with the used type of fuel. Some not directly the fossil fuels, the other options can be used, and our target is like that. And our we are continuing about the R&D part, but we are planning to also introduce an additional product with ultra low carbon cement. It's just it's not only based off changing the fuel, it's also just including some other supplementary cements that will be and the other options. And that product will be less than 200 kgs. 200 kg CO2 per ton of cement. And that the main contribution based on the effect of calcined clay, because in process effect of CO2, it's zero with calcined clay because it's not included any carbonated component inside of it. On the fuel side also, we completed the research studies. Now we are planning to implement it in next month. We also decrease to minimize the combustion CO2 emissions. And by that way, we could get a nearly net zero cementitious material. And adding that one helped us to create ultra low carbon cement. I want to introduce to you our first plant in Africa, the first calcined plant in Africa also, just fully integrated, calcined clay integrated cement grinding plant and fully greenfield constructed. Commissioned in the mid of August this year at Abidjan. And the capacity is up to 300,000 tons per year. It's related about the composition of raw clay, its moisture content, and the other issues. And also, its grinding capacity is 2,400 tons per day cement grinding capacity in the plant. As you could see in here, it just there's the main stock house in here because of the rainy and tropical weather conditions of West Africa. We just build a big stock oil in the middle of the plant. And then the calcined clay line in here, the cement plant line in here. Calcined clay, it's just clay preparation units, the filter group and feeding unit, and just rotary kiln, rotary dryer, and then rotary kiln in a coupled design, and then the cooling unit in here, then just calcined clay stored in here, and then sent to cement inside. What are achievements and experiences? I want to share a little bit of detail about that. More than 9,000 tons of dehydroxylated clay already have been produced. And yeah, I think it's around 970, 900, it's just near to 10,000 tons yesterday on the field, and some of them also used in blended cement. In our first remarks, it's just there are many issues and people are sharing and technology suppliers giving, but in the exact field results, we saw that it's the specific heat consumption is between 550 and 750 kcal per kg. Its range is high, but it's related about completely raw clay, moisture content. There are many effects on it, and we are on the optimizing stage. we believe that we could keep it in just around 550, 650 kg between. When we look on the specific electricity consumption, it's between 18 and 23 kilowatt hour per ton. That deviation also related about the capacity options. It's one of the most critical points is everyone talking about the producing calcined clay, calcining, dehydroxylation and heat and other things, but just more complicated part, it's just using and creating a blended cement by using calcined clay, because it's not a crystallized product, it's not homogeneous in physical characteristics. Some portions goes very fine, the other kept in coarse. It should be studied specifically, and we also did that R&D studies, and we could achieve that good results by that way. And we could now control the water demand and other quality options. And still we are doing some investigations to improve it, but it's much more complicated. And also preparation and cooling stages must be robust and effective and reliable. We just saw it and experienced it in that first plant, especially in the preparation. You don't need to make it so complicated. It should be a good quarry and good sieving and separation need to be done on the quarry, and then there need to be a robust, reliable equipment in the just size reduction and just making the material ready to feed the combustion process. On the other side, cooling stage, it's also critical. Still, we have been experiencing it since the beginning. It's a problem for us to solve it. And now we are working on it, and we will be just solve it in next month. Cooler should be just need to be designed properly about that. According to that issues, also there are many replace and revamps applied besides the main suppliers designs. We changed in that plant, and still we have some modifications available. We will do it in the first half of next year, and our expectation is much better results and much effective results at 2021. At that point, there's not a typical design to select a rotary kiln, rotary dryer, or a flash calciner. It's related about your material chemistry and physical characteristics, minor components, impurities, layout limitations, fuel energy accessibility and its costs, and the expectations from products will define the process concept. There is not a typical design. You should have to just select it and use it. It should be tailor-made. That's the critical, and need to be studied well and designed on it. We experienced it in the first project, and then we did it much better in the second one. When we just give an indicative issue about that variable costs of calcined clay stage, producing calcined clay, the most critical part is, as all we know, that it's the heat energy. But the heat energy also can be optimized, but by different options. If you have options available, accessibility, it directly affects the cost of calcined clay, and it creates a big advantage also. And we are also working on it, and we start to get good results about that, and we'll be much more better next year. We have some projects about that. Just some operational criteria I want to just introduce about that. Quarry survey, just issues and mineralogy, clay preparation, pyro process, quality, color, dedusting and filtration, and cooler design is also important to just select it, as I told on the previous slides. Now I want to show that some visuals from the plant. As you could see, it's directly taken on the Abidjan plants. In here, just clay preparation units in the left side in the order, and then it comes to kiln in that part, rotary kiln, rotary dryer, kiln hood, filling belts, and kiln. Our aim and just the target is to reach 40% CO2 reduction, 40% CO2 reduction with additional fuels and alternative fuel options with high blended cements, 30% decrease in energy consumption, and also indirectly effect of heat consumption due to decreasing clinker amount, and less heat consuming calcined clay, 20% of cement, less per ton of cement. And you could see the first product. It was in our hands on 16th of August 2010. The other project is also it's also important for us in Cameroon, in Kribi, and will be commissioned in the last quarter of 2021. Again, it's 720 ton per day calcined clay capacity and 2,400 cement grinding capacity based on flash calcining option. We did that, some pilot studies and mutual R&D jobs with and some pilot scale applications with the supplier of that plant, and all that studies completed and the constructions are going on. Now I want to share a short video about our Thanks all for listening. Yeah.
Thank you, Berkan. Thank you very much. We're running against a very tight schedule because we have another presentation coming up in 10 or 15 minutes. So I'm going to try and get in maybe 2 or 3 relevant questions. Again, loads. So we will actually pass all the questions on that are not answered to Berkan and other speakers.
Okay.
I think questions you've already answered about why not to use cyclones with a rotary kiln. You answered that. Also, there was another question which was suggesting that the LC3 concept didn't have the permissions in West Africa, but I think you've already answered that. You have the certificates, you've shown those, so I presume that answers that question. There's another question here. Please clarify where you need a reducing atmosphere in order to control color.
That details also explained, but basically I can say it. It's, as I said, it's related about iron oxide content. The all clay minerals, a minor amount also can be available, but if iron oxide heated up over 500 degrees, if it's then while cooling that material, if it's oxidized in oxidizing atmosphere, then it creates hematite and its color becomes, hematite is a reddish color mineral. That's the reason. If you put it in the reducing atmosphere, you're just generating magnetite rather than hematite, and magnetite is a darker color. That's the issue basically.
Okay, I'll try and keep these questions to the ones specifically to do with your presentation, because I know that after this there are some, we're going to do presentations on the equipment and how the plant was set up, etc. So we can maybe keep them for that. The next question is from Aranda. Any experience info in high smectite, low kaolin content clays from this industrial perspective?
Just in clay minerals, also not including only kaolinite. It's some illite, montmorillonite compositions also available in that composition. Right. They also affect positive effects on quality and reactivity. Also silicium dioxide. It's just quartz. It's also effective. We are not talking about the pure kaolinite.
No. Okay. A note from Tony Hadley, who's well known in Africa. He's done a lot of work with Lafarge and with other major cement producers in the continent, including Dangote. He says, well done. You will trigger a great reduction in global CO2 emissions. And he says for the majors to act. I think they're aware of the situation already. Will you be able to use biomass in Abidjan once the process is stable?
Yeah, can be. It's also a potential. One of the other advantage of Africa, one of the reasons of why Africa is also the biomass potentials and other alternative fuel options.
So in other words, you have no problem with there'll be no problems with the amount of biomass that you can use. Okay, just a couple more because we do need to move on. One is very simple. What is the company name in Africa, or are you keeping that confidential?
Our company or supplier, you're asking?
No. Is it going to be an OYAK company in Africa, or is it going to be a national name in Abidjan or in Cote?
Yeah, it's just we are using a Simpor name again, but Simpor Africa under Simpor.
There will be Simpor. Okay, no, that's fine.
Simpor,
that
Simpor
answers the
name.
question. Okay, fine. Last couple. What was the biggest problem from John Klein? What was the biggest problem during startup?
I can answer that. It's just the biggest problem we lived in just the cooler part. It's just the cooler, and there are some mechanical and other problems available. As we know, it's the first concept, but there are some problems on that. And but we are able to just solve it. Also internally, we have some modifications and other things, but we leave problems in the cooler and also clay preparation units, supplied equipment on it. And also just I want to that at that point that just there are some rumors available in the industry, but our suppliers just need to be approved by ourselves. We are approving them. Don't accept. Need to be our acceptance. There are some shares about that, the supplying OYAK about calcined clay, but it's just only accepted companies that work with us.
Okay.
Clarification.
I think we have to move on, Berkan. I think you're joining us for the next panel anyway, so I might actually try and put the couple of these questions if we have time in the next section. Maybe the last one is: are you importing the limestone to mix it with calcined clay clinker? For this project, or are you just going with the the calcined clay that you have, or the clay that you have locally?
Yeah, but limited and just not high quality one.
Okay.
Starts to decrease it.
Okay, great. Okay, well, I think we have to close it there. Thank you, Berkan. It was really interesting. We have loads of questions, as I say. We'll try and put some of them perhaps in the next session. And if not, any questions that are not answers, we'll send them on to you, and you can perhaps answer them directly. Thank you very much.
They can also just reach to us. Just read them there.
Yeah. We certainly will do that. Thank you very much for your presentation. If you could say thank you to Mr. Çelbayek as well for his cooperation in making available all this information. And I'd like to say thank you and goodbye. Thank you.
Thank you, Malcolm.